Hello, it's Keith here, and this is lesson 35 of the simple series on my Z80 assembly programming tutorials, and we're looking at the Sega Master System. Also works on the Game Gear today, and we're looking at sprites, hardware sprites, sprite clipping. Now last time we drew our chibiko mascot, that's the character you can see here, a character in the wrong colours, but never mind, and we drew it with the tile map, so we simulated the sprite by drawing a grid of tiles. Now this time we're drawing the character in entirety, and we're using hardware sprites, and the benefit of this is we have nice smooth movement and we can go off the screen partially. The disadvantage is we can't have as much as we want on the screen necessarily. Each of the 8x8 blocks in this sprite is using a different individual hardware sprite, so we're using 36 hardware sprites to draw this. So if we had thousands of objects on the screen, then we might run out of hardware sprites. It would be a problem. So there's limitations with this, and as I've said before, if you can make a simple game without using hardware sprites, I'd suggest you try and do it if you're getting started, but hardware sprites of course are far superior. Now because we're using hardware sprites, we can have very smooth movement here, and you can see our character can go off the top of the screen, and we can also go off the bottom and the left and right very smoothly. However, when we go off the left hand side of the screen, you will notice that the character disappears in chunks. You know, you can see here that there is a sort of very noticeable there's a sort of gap there where there's no sprite being drawn, and you might think that that's a glitch in my code. Now it's not really a glitch in my code. There is a limitation on the Sega Master System that the X coordinate of the sprite has to be from 0 to 255, and the screen is 256 pixels wide. This means there's not enough bits of the X coordinate to allow fully smooth movement on the entire horizontal axis, and so the only option that you've got is that there is an extra bit you can turn on in the VDP registers, and it will actually hide the entire far left strip of the screen. So there will be a basically black, or in this case the border is blue, so there will be a blue strip on the left hand side, and that affects the sprites and the tile map, and that would allow you to hide the that sort of glitchy area, if you will, that you can see here, where it's not changing in a consistent way. You would then have the consistent sprite movement. You would just lose 8 pixels of the screen, so it's up to you which one you prefer. But anyway, we're going to look at the code that does this today. What we're not going to look at is we're not going to look at the stuff I covered last time. I'm not going to discuss really the logical units, except to say that my coordinates are logical units. One logical unit is 2 physical pixels, and 4 logical units are 1 8x8 tile or sprite. But I'm not going to go into it any further than that, and I'm not going to go into the details of the sprite clipping, the cropping routine that I'm using. So we'll look at it briefly where it's changed, but if you need more details on it, please see lesson 34 when I went into it in a great amount of detail. So we're not going to cover all of that today. Anyway, let's get over the code. Let's take a look. Okay, so this version is based on the previous version, so we've got our sprite H clip again. We've still got the visible screen bank here, but I'm not really using that this time. We do have a new hardware sprite number because our character is 48 by 48 pixels. Last time we were making that up out of tiles, and this time we're using 8 by 8 pixel tiles, and so we're going to need to track the hardware sprite number of each one of those 8 by 8 pixel patterns that are being shown to the screen in the form of a hardware sprite that make up the larger character. So we're going to use H sprite number to track that. Now the visible screen width, you'll notice we're subtracting 8 from the minimum X here, and that is so that we can handle the sprite clipping as our sprite goes partially off the screen. We still need to sort of calculate it to do that, so we've just made a slight tweak there, so to speak. Now the rest of the code here, I mean, most of it hasn't really changed here. You will notice that I've included in the registers defining the screen layout. If we want to hide the left-hand strip as I described here, we can enable this second line that's got that extra 1 bit enabled. If I just unrem that and I rem this out, if I press the right key, that is, and we just run this again. Well, now here is our example again, but now you can see that that left-hand 8 pixel block is removed, and as I say, it's always invisible, so you don't get the weird glitchy sprite, and that is to compensate, as I say, for the fact that we are only using an 8-bit X coordinate in hardware. So it's not a glitch in my program, it's actually the hardware sprites only use a single byte for the X coordinate. Now here is the do crop routine, and basically all that's changed here is we are now basically when we are doing our cropping of the top and the left, we are taking any bits that we were previously removing, the bottom 2 bits, and we're XORing those. And this is so that as our sprite goes off the top of the screen and we start removing sprites and patterns, we need the remaining parts to end up in a consistent position to compensate for the bit that's been removed. And so we're having to, basically, as we remove one 8-pixel tile, we're having to add 2, 4, or 6 pixels. These are logical units, so one logical unit is 2 pixels. So we can't move in individual pixels with this code, but it's smooth enough, you can't really tell. But as I say, we're basically inverting the bottom 2 bits of the x coordinate in logical units, and that is allowing the sprite to move smoothly as bits of it are effectively being removed from the drawer. So you can see that on the top, and you can see it also on the left. Now we're having to do some rounding in various places to convert to a number of patterns, or tiles if you prefer. As I say, we're not using the tile map anymore, but we're still using the same pattern data, the same 8x8 pixel blocks, and that's the hardware sprites we're using. So again, we are still having to round it into a number of patterns, even though we're no longer working in sprites. And our final calculations, converting from logical units, we're now converting the x and y position into pixels, so we're effectively multiplying those by 2 to get a multiple of pixels, but we are dividing the width and the height by 4, effectively giving a number of tiles or patterns, because as I say, the hardware sprites are 8x8 pixels. Okay, now our do sprite routine, where is it? So we've got our draw player routine here, and that does the do crop, and then it uses this fill area with sprites routine. Now if we just go back over to the documentation here, you can see we've got a chart here of all of the data within VRAM that define our sprites. So each sprite has 3 bytes in total. It has 1 byte for the Y position, so that can go from 0 to 255, and our screen's only 192, so we've got very smooth movement going down. Now units around 255 are actually negative, so that's how you make sprites appear partially off the top of the screen, but our X coordinate is just a single byte, so we can't do that horizontally, which is why we have that option to hide the far left strip of the screen there. Our N is the tile number, so we've got these 3 bytes that we need to change, and they're in rather strange memory positions. Seem a little bit odd to me, but whatever, we can work with that. I guess it's so that if they'd used 3 bytes, it would maybe a bit harder to multiply up, maybe, and if they'd used 4, they would have had to skip one, so maybe, I guess it's something like that. Seems a little bit odd though. Anyway, that's what we're going to have to work with, so that's what we will work with. So our fill area with sprites routine is very much a mimic of fill area with tiles. So we're going to calculate from our hardware sprite number, which we will start off as 0 at the start of each draw. So we reset at that every draw, and then we start allocating hardware sprites to each 8x8 pixel block. So first of all, the base is 3F00, and there's 1 byte per hardware sprite. So we are specifying our destination VRAM address here with the top byte as 3F, and then we're adding 40 to that in hexadecimal, and that's just so that we have a writing port. So we're selecting the VRAM destination here, and that is going to select basically the Y position for whichever hardware sprite number we currently have. And then we're writing our Y position from C here. It's in pixels now, of course. And then what we're doing next is we are getting the hardware sprite number again, multiplying it by 2, and we are adding hexadecimal 80, and this is so that we get the coordinates here. So you can see here there's 2 bytes for each sprite there, the X followed by the N, and we're going to write both of those, and they start at memory address 3F80, and that's why we've got these calculations here again, plus hexadecimal 40 to the top byte to define this as a writing VDP port here. We're then writing our X position here, and we're then writing our tile number, just a single byte for the tile number, so we can only use up to 256 tiles. The other tiles can be used for the background tile map, but they can't be used for the hardware sprites. After each sprite, we are incrementing our hardware sprite number, and we're incrementing our tile number that we're using, because this 36 by 36 chibiko bitmap always assumes the tiles are consecutive. If you want it to be more complex and remove repeated areas, you need to have a miniature tile map and read in from that. I did that with my Suck Hunt game that used a miniature tile map for each of the sprites, if you will. It only used the tile map, it didn't actually use hardware sprites, but the procedure would be the same. You just need to have some kind of lookup table for the hardware sprite patterns you would want to use. Now we're then moving across the screen 8 pixels. We're updating the X position for the next hardware sprite, and we're repeating until we've done a line. Once we've done a line, we are skipping any sprite patterns we don't need. This is for the case where our character is partially off the left or partially off the right. We would need to skip some tiles after each line. We're drawing horizontally and then moving down in a zigzag format. So we are skipping any sprites that are not needed, any numbered patterns here, and we're moving down one line and we're repeating again here. So this loop is done to fill in the hardware sprites. Now there is one limitation though. Now if that is all we did, that would work quite nicely when our character was entirely on the screen. That looks nice. However, when we start to go off the screen, we get these weird trails. Now what these are is, this is one of the things that make hardware sprites a little bit more tricky to work with. When we give a hardware sprite an X and a Y position, if we simply don't need it anymore in the future, like now when our character is no longer needing the same number of hardware sprites, that old position is still going to stay there. So we need to actually do something with it. Now here the characters come back on the screen, so those hardware sprites are being used again. But if they weren't, then we would actually need to give them some kind of zero position. Now what we actually do, as far as I'm aware, is up to us. But basically what I'm doing is I am giving all of the hardware sprites a Y position of 200, which means they're off the screen. You could also give them a sprite pattern that is blank, whichever works for you. I don't think there's any problem with either of those. But all I'm doing here is I'm sequencing through all of the 64 hardware sprites, and I'm setting all the unneeded ones to a tile number of 0 and a Y position of 200, and that is making them invisible to the viewer, and that's how we're resolving that issue. So there we go. So that's actually all I'm covering today. So nothing particularly complicated really. I've got other tutorials on hardware sprites if this one was a little bit tricky for you. Take a look at my Y-Quest game, a little game that used hardware sprites on the Sega Master System and Game Gear. That's another great one if you want to get started. And in the platform specific series, I do have another tutorial on hardware sprites as well. So more content out there if you need more background on this if you're not quite confident with it yet. But anyway, as I always say, go to the website, download the source code, the build scripts, and you are welcome to use this in any way you want. So, you know, if you want to use it in your own games, if you manage to make some kind of amazing game out of it and $100 billion in the process, you're welcome to it. I'm sure you've earned it and you don't need to give me credit. Anyway, hope you've enjoyed what you've seen. Thanks for watching and goodbye.